There are many different types of volcanoes and volcanic eruptions on Earth, and they all generally contain similar characteristics to others that are of the same type. A few of these characteristics include what is fueling the magma chamber, how the eruption itself occurs, and how explosive and destructive these eruptions will be. Alongside the variance in volcanoes comes a divergence in the types of magma they consist of, and in this video I will attempt to break down what the different volcanic types are, the differing types of magma contained within these volcanoes, and more importantly, why the type of magma is incredibly relevant when addressing the explosivity of a volcano. I'll attempt to do this in an easy to understand way. By the end of this video, you'll understand why some volcanic eruptions are horribly devastating and powerful, with some akin to nuclear bombs, and many that are much stronger, to the gentler volcanic eruptions, some of which have very minute explosive qualities to them. There are three main classes that separate volcanic eruptions. These three classes are magmatic, phreatic, and phreatomagmatic types of volcanic eruptions. The first is the one we're all familiar with, the magmatic types, which are the ones that spew out sizable quantities of molten rock upon the surface of the Earth due to a buildup of pressure within the volcano's underground magma chamber. This occurs when the pressure reaches levels beyond what is able to be contained within the magma chamber itself. These types range from the relatively small lava fountains found on Hawaii to the ultra-Plinian eruptions, also commonly known as supervolcanic eruptions. Thermal expansion is the main player of how and why these types of volcanoes erupt. So this video will be focusing on the magmatic type of eruption, as it is the family with the most differing types of volcanoes. The phreatic and phreatomagmatic types will be covered in the following video. I'll be sorting the following types based on their explosivity, and we'll be going from the least destructive to the most destructive magmatic volcanic eruptions that we have discovered thus far. Keep in mind, volcanoes can be a combination of these families, but I'll go more into that in part 2. The most important bit of knowledge to keep in mind about volcanic eruptions is this one key factor called the silica level. Silica, when defined, is a hard, unreactive, colourless compound which occurs as the mineral quartz and is the principal constituent of sandstone and other rocks. I know, this doesn't sound too interesting yet, but this is the one main factor that separates the littlest and least destructive eruptions from the largest eruptions we've ever discovered on Earth. The silica content within magma has a direct correlation on the explosivity of a volcano and its subsequent eruption. High silica contents create a very thick, viscous type of magma. Volcanoes that erupt in a very large manner, such as Tambora or Yellowstone, contain exceptionally high levels of silica in their overall magma composition. The overall level of silica is determined by the type of rock that makes up the bulk of the magma within a volcano's magma chamber. Different rocks contain different levels of silica. Rhyolite and granite are two examples of high silica rocks. Rocks of volcanic origin with more than 65% silica are classified as felsic rocks. Between the 55 and 65% silica mark, we find rocks that fall within the classification of intermediate, and after this, we approach mafic rocks that contain between 45 and 55% silica. Finally, the last category is labelled ultramafic, and these rocks contain less than 45% silica. Volcanic eruptions that are fueled by the two mafic varieties of magma are the weakest of all volcanic eruptions in terms of their explosivity. So, the final two categories contain a high level of mafic minerals in their overall composition, such as high levels of magnesium and iron, and thus owe their name to that. Volcanoes that so famously make up the Hawaiian Islands occupy the mafic categories, and at this level we see magma that is of fluid consistency. This type of fluid magma is able to travel vast distances and creates lava rivers and lakes in the process. This type of travel would be impossible for the thick, viscous type of magma that is found within the Earth's more explosive volcanoes, such as Tambora, Yellowstone, Lake Toba, and so on. Another important thing to note is the temperature difference between mafic and felsic rocks. Molten felsic rocks sit between 650 and 750 degrees Celsius, or 1002 to 1382 degrees Fahrenheit. This temperature also works to contribute to its thicker viscosity, whereas mafic rocks are much higher in their temperatures, at around 950 degrees Celsius or 1740 degrees Fahrenheit and above, which only works to further contribute to a lower viscosity level and a more fluid consistency. The overall viscosity determines whether or not the many volatile gases that are released when solid rock is heated to the point it becomes fluid remains within the magma chamber or is able to escape it. A thick viscosity has the ability to partially or even completely trap these volatile gases within the magma chamber, and as this cycle repeats and more magma from within the earth fills the magma chamber, over time this builds up immense pressure that eventually hits a critical level and culminates in violent and destructive volcanic eruptions. Low silica levels leads to a low viscosity, which creates magma that can sometimes be close to watery in its consistency depending on the silica level. Because this magma is so fluid, the gases fail to remain trapped within the magma and are instead able to find their way up towards the surface. This action depressurizes the magma chamber and prevents it from building up pressure to destructive levels. We see a great example of these types of magma in the many Hawaiian volcanoes, and you can very clearly see the strong difference between these types of volcanoes versus those such as Krakatoa, which has a high magma viscosity and produces really deadly eruptions. So silica and its effects on magma viscosity is a very important factor in whether or not an eruption will be explosive, destructive, mild, or gentle. One more very quick clarification. Magma is the term used when these types of molten rock are still below ground, and lava is what it is called when it reaches the surface. Okay, now we can get into it. Magmatic Eruption Type 1, Hawaiian Eruptions. These are the calmest types of volcanic eruptions, characterized by a very low silica content. Like previously mentioned, they fall in the mafic categories, so the silica level is either below 45% or between 45 to 55% depending on the volcano, location, and the rock types that are fueling the magma chamber. Because of their mafic category, the types of rocks that fuel Hawaiian eruptions are rich in iron and magnesium and create a magma that is very runny in its consistency with a very low viscosity level. These types of eruptions are characteristic of Hawaiian volcanoes and thus earned its name from them, but this category extends to any volcano in any region of the world that displays this characteristic type of eruption. Most geological books usually list the magmatic types of volcanic eruptions that I'm going to cover in this video, but I've noticed some websites also contain a type of eruption called Icelandic eruptions, which are more or less synonymous with Hawaiian eruptions. The key characteristic of them being they erupt from fissure vents and parallel fissures, which go on to build lava plateaus like this. Hawaiian eruptions, however, are also known to do this, so I wanted to point that out just in case there is some confusion amongst those who might have heard of the term Icelandic eruption. Both volcanic eruptions are fueled by mafic molten basalt. Some key differences between the two are the geographical location where the volcanoes dwell and the geological setting. Iceland contains many subglacial volcanoes that are covered by ice. Sometimes they are covered by many kilometers worth of it. But we are bordering into the territories that we will cover in episode 2, so let's move on. Hawaiian eruptions contain a very fluid basalt type of lava that oozes its way out of the earth and due to its almost watery consistency contains a very low gaseous content. Generally, the volume of ejected material from Hawaiian eruptions is less than half of what is found in the other eruptive types that we are soon going to cover. Basaltic type lava is able to steadily creep across the land and over time can form large hills or mountains that have a very gentle incline and are referred to as broad shield volcanoes. They are named so because of their resemblance to a medieval warrior's shield. These mountains can grow to be quite large in size. The reason for this is the low viscosity lava's ability to travel vast distances that are far from its eruption source, where it eventually cools down and slowly builds these giant yet easy to trek mountains over time with each subsequent eruption. For example, Hawaii and its neighbouring islands were constructed entirely from these types of eruptions. that, over time, allowed it to rise up from the ocean to become the beautiful islands we treasure so much in present day. Unlike most other volcanic eruption types, Hawaiian eruptions normally don't occur from the summit of mountains. Instead, they often occur at vents around the prior summit, and from fissure vents, which are known to radiate out of the center of it. Fissure vents are also sometimes referred to as a curtain of fire, and for a very good reason, as you can see in these pictures. These die down as lava becomes concentrated to just a few of the vents. When these types of eruptions do occur at central vents, it is often in the form of large lava fountains, which can be sporadic, continuous, or a combination of both of these elements, and can reach heights of hundreds of meters or more. The lava particles released from these fountains usually cool prior to making contact with the surface, which creates a cindery scoria fragment. If there is an unusually high amount erupted, it won't cool prior to contacting the surface again, and will form spatter cones, which look like this. The creation of lava lakes is due to these types of eruptions, but they are quite rare, with only a handful of lakes currently existing in the world. These eruptions can last for a very long time. Some of them can last for a few years, others decades, and some last for centuries or thousands of years or more. Magmatic Eruption Type 2, Strombolian Eruptions. Named after the Stromboli volcano in Italy, and not the deliciously cheesy meal to my utter dismay, Stromboli has been erupting continuously for centuries. These eruptions are driven by the bursting of gas bubbles within the magma chamber. These bubbles accumulate and coalesce into larger bubbles called gas slugs, and grow large enough to rise through the magma column towards the surface, where the difference in air pressure causes the bubble to burst with a loud pop, which causes magma to be thrown into the air. Strombolian eruptions are a form of low to moderate viscous basaltic lava, with a higher than normal silica content compared to Hawaii's form of basalt, with it reaching the upper range of mafic to early intermediate in its silica level classification. Because of the high gas pressures associated with this lava, continued activity occurs in the form of episodic explosive eruptions, accompanied by very loud blasts, which can occur every few minutes during an eruption, but typically eruptions are pretty short-lived. When they do occur, eruptions of lava are ejected high into the air, and some lava columns have been measured to have reached hundreds of meters in height. These eruptions can continue for thousands of years. Some other factors that separate these types of eruptions from the Hawaiian ones is the noise produced, the fact there are no sustained eruptive columns, and also there are barely any molten lava flows, because the viscosity surpasses this ability. This is a great example of exactly what silica content does, and is the predominant factor causing these differences that we find in the Strombolian types of eruptions compared to the Hawaiian ones. Recently, the Stromboli volcano has erupted at levels higher than the Strombolian classification, and this is worth pointing out due to the fact that volcanoes aren't always consistent in their eruptive styles, and the rocks that make up the magma chamber can actually differ between eruptions. Some of the larger volcanoes can erupt at a Strombolian eruptive level, and some of the smaller volcanoes that are known for weak eruptions can suddenly roar forth at one level or multiple levels higher than what they are known for. The key here again is the silica level and what rocks are filling the magma chamber. Magmatic Eruption Type 3, Vulcanian Eruptions. Vulcanian eruptions are named after the volcano on the island of Vulcano, which is located just north of Sicily in Italy. The magma chamber that makes up Vulcanian eruptions falls within the intermediate silica type, so it contains a silica level existing within the range of 55 to 65%, and thus the magma viscosity is much higher. The higher magma viscosity found in these types of eruptions works to trap volatile gases, resulting in the buildup of pressure over time. When the pressure reaches a critical level, these eruptions occur, blowing the ground above it into the air, upon which the magma then surfaces as an explosive eruption. They are fueled by molten andesitic and acidic rocks. At this point, we begin to see crystallization within the rocks post-eruption after they have cooled down and solidified due to the higher presence of silica. Andesite on its own contains a silicon dioxide level of 57 to 63%, and dacite contains between 63 to 68% silica. The level of silica present within the magma chamber of these eruptions results in explosive eruptions and eruptive columns that can often reach between 5 and 10 kilometers or 3 to 6 miles high. In general, the type of eruptions produced are characterized by a series of short explosions, lasting a few minutes to a few hours, that eject volcanic bombs and blocks, dangerously hurling them in all directions. These types of eruptions are known for forming lava domes, which is normally a relatively circular, mound-shaped protrusion that is formed from the slow extrusion of viscous lava. So, as you can see, as we are going up the viscosity level, lava loses its ability to flow and travel, and is at this stage confined to forming structures immediately surrounding the eruption site. These lava domes normally become worn down from these types of eruptions and actually collapse, which causes a very dangerous and destructive amount of pyroclastic material to surge down the volcano's slope. Following this type of scenario, yet another lava dome is rebuilt, and the cycle continues yet again. Strangely, unlike other volcanoes that are strictly magmatic in their category, Vulcanian eruptions have at times occurred due to an interaction between the magma chamber and groundwater, suggesting some kind of phreatomagmatic relationship. However, we'll cover this more in part 2, but I thought it was worth quickly mentioning. Magmatic eruption type 4, Peléan eruptions. Peléan eruptions are where things step up a notch and start becoming very violent. These eruptions have the ability to cover entire cities, scorching anything living within it with deadly pyroclastic flows. Peléan eruptions involve a large amount of gas, dust, ash and lava fragments, which are blown out of the volcanic crater due to the collapse of a rhyolite, dacite and andesite lava dome, which creates a giant eruptive column in the process. The magma chamber of Peléan eruptions sees the silica level occupying the upper end of the intermediate category into the felsic level due to the inclusion of rhyolite, which itself contains over 69% silica. These eruptions are associated with a strange phenomenon known as a lava spine, which is a vertically growing monolith of viscous lava that is slowly forced from a volcanic vent. Lava spines normally serve as a very useful sign that the volcano is close to erupting. During eruptions, a very dangerous and incredibly fast-moving pyroclastic flow occurs, and moves down the side of the mountain at high speeds, normally ranging from at the very least 150 km per hour or 93 miles per hour or more. In the past, these eruptions have caused enormous damage and have led to massive casualties, with one eruption in this category taking the lives of 30,000 people, and this level of damage occurred in only a few minutes following the descent of a pyroclastic flow. Because Peléan level eruptions are fueled by andesite, dacite and rhyolite, the high level of silica leads to a magma viscosity thick enough to build up an enormous amount of pressure, leading to one gigantic eruption, rather than several smaller ones, like we saw in the other 3 types of magmatic volcanoes. Magmatic eruption type 5, Plinian eruptions. We have now reached the category where the official volcanic bad boys that the majority of history's most dangerous yet famous volcanoes dwell within. This is where eruptions get really destructive. These types of volcanic eruptions are always very large and incredibly violent. Famous volcanoes such as Mount Vesuvius and Krakatoa are best known for their disastrous Plinian level eruption. The name itself comes from Pliny the Younger, a Roman man who witnessed the eruption of Mount Vesuvius in 79 AD, and gave a detailed account of the characteristics found within these types of eruptions. Plinian eruptions can itself be broken up into 3 subcategories, those being subplinian eruptions, Plinian eruptions, and the ultraplinian eruption. To clarify very quickly, subplinian eruptions fall within magnitude 3 to 4 on the Volcanic Explosivity Index, making them comparable to Vulcanian and Peléan eruptions in their destructivity and overall tephra released. Plinian eruptions are the ones most people have in mind when they think of volcanoes and volcanic eruptions. Ultraplinian eruptions are the most devastating and destructive form of volcanic eruption, 8 is the final number and is where the largest eruptions that have ever occurred on our planet dwell. The power of the mighty Plinian eruption begins with dissolved volatile gases that are stored and increasingly accumulated within the very large magma chamber that possesses a very high silica content, fueled by molten dacite and rhyolite. As the gases accumulate, pressure steadily increases, and the bubbles within the chamber actually agglutinate, which essentially means they bond together very firmly and form a single mass that contains a massive coagulation of volatile gases. Once bound together, they set off a chain reaction. This scale of bonding normally occurs once the magma chamber reaches roughly 75% of its total volume. The explosion and subsequent eruption leads to the violent propulsion of magma, which surges up the volcanic conduit towards the surface, where, upon reaching it, an enormous explosion occurs that forcefully propels tephra towards the sky, forming a gigantic eruptive ash column that reaches unbelievable heights. Some of these have been calculated to have reached at least 45 kilometers or 28 miles into the atmosphere. The velocity of this is controlled by the gas contents of the column and is usually propelled even further by low-strength surface rocks that crack under the pressure of the eruption and form a flared structure, which further facilitates this. The part of the column highest in overall density is the bit directly above it, and it is being driven internally by gas expansion, leading to it losing concentration the further it spreads. The heat and subsequent thermal expansion and convection of the volcanic ash drive the plume further up into the stratosphere, where the very top of it is then sent in the direction of the prevailing winds, spreading it to incredible distances around the globe, but do the most damage to areas within 50 cubic kilometers or 12 cubic miles around the site of the eruption, which become covered by a thick layer of many cubic kilometers worth of ash. Some Plinian eruptions are strong and large enough to send the ash cloud around the globe, with a reach that can affect countries great distances from where the eruption originally occurred. The eruptions themselves can last anywhere from a few hours to multiple days. If a Plinian eruption occurs for an abnormally long amount of time, this is because it contains more felsic material. Quartz on a chemical level is literally just silica and oxygen, so the magma within these chambers that contain a higher concentration of these materials have a dramatically increased viscosity, leading to eruptions lasting longer and to them containing a higher level of destructivity, simply because of that reason. The deadliest threat faced by those unlucky enough to be in the vicinity of a volcano during a Plinian level eruption isn't the giant toxic ash plume released, or even the massive lava bombs that are hurled in all directions, with some of them being as large as a car or even larger. Whilst these can be fatal for obvious reasons, the deadliest and by far the most scariest characteristic of Plinian level eruptions and above are the terrifyingly massive pyroclastic flows that are released usually when the ground collapses upon the rapidly emptying magma chamber. Although it doesn't need this phenomenon to happen to exist, but when it does, this emptiness causes a ground instability, and when the collapse inwards occurs, out comes a deadly surface-hugging cloud of molten material that surges forth at a ridiculous speed, usually approaching 700 km per hour or 430 miles per hour in its speed. To make matters worse, if that's a possibility at this stage, which it definitely is, if the volcano contains snow or ice deposits, the mixing of tephra released by the volcano can lead to an extremely dangerous event known as lahars, which are essentially fast-moving mudslides with a consistency of wet concrete that move at speeds akin to the rapids that are found in fast-flowing rivers. Lahars are extremely destructive. They can flow tens of meters per second and have been known to be up to 140 meters or 460 feet deep. Lahar flows tend to destroy any structure in its path. To surmise, Plinian eruptions are a bad situation to find yourself caught up in, but surprisingly, they are nothing compared to the notorious final magmatic eruption type. Many of you know where I'm heading with this. Magmatic eruption type 6. The ultra-Plinian eruption, more commonly known as the supervolcanic eruption. The ultra-Plinian eruption goes more than just one step further. It goes hundreds of thousands of steps further. Whilst Plinian eruptions could erupt anywhere between 0.1 cubic kilometers or 0.02 cubic miles worth of tephra at the sub-Plinian level, which ends at the 1 cubic kilometer or 0.24 cubic mile mark, after which the Plinian level eruptions take over and continue all the way up to the 100 cubic kilometer or 24 cubic mile mark, where the ultra-Plinian level finally begins and goes beyond the 1000 cubic kilometer or 239.9 mile mark to an undefined number that is increasingly getting larger as more supervolcanic discoveries are found on the scarified Earth, where they are able to hide so amazingly well. For example, the La Garita supervolcanic eruption released at a minimum 5,000 cubic kilometers or 1,199.5 cubic miles of fallout, and this is at best a guess into the minimum amount released. The reality is the likelihood that this eruption released far more than what is predicted is very, very high. The problem is, eruptions at this scale have gotten far too large to conclusively get an accurate estimate, so we have to make do with the minimum overall estimates instead. That's how freaking big they are. Volcanoes at this scale begin at a place where the line is drawn at the end of the most strongest Plinian eruptions known to man upwards. No, I'm not talking about Mount St. Helens, which released 1 cubic kilometer or 0.2 cubic miles of tephra, nor am I talking about Krakatoa's disastrous 1883 eruption, which released 25 cubic kilometers or 6 cubic miles worth of tephra. I'm talking about volcanoes such as Tambora's 1815 volcanic eruption, which was the largest volcanic eruption ever documented in modern times. These types of eruptions release over 100 cubic kilometers or 24 cubic miles of tephra, and this is the defining stage where the label of supervolcano begins. These types of eruptions, even at their smallest, release enough tephra to affect the climate of the entire planet, which the 1815 eruption of Mount Tambora was notorious for doing. It does so with the release of gigantic ash plumes that shroud a massive area of land, making it unlivable for people, animals, and even plants. It releases pyroclastic flows at an enormous and almost unimaginable scale that are able to travel massive distances, burying both surrounding lands and even distant lands under layers of ash in the process. So, to further differentiate between the VEI-7 and VEI-8 volcanoes, volcanic structures responsible for releasing hundreds of cubic kilometers still retain a typical volcanic shape, referred to as a stratovolcano, which is the steep conical shape most volcanoes are associated with. And as the eruptions get larger and larger in scale, these types of volcanoes begin to cease existence as the defining visual feature and are instead replaced by giant calderas, which are huge depressions in the land that cover enormous distances. In fact, they are so large that if you were standing in the middle of it, you wouldn't even notice that you were standing in a depression or even a caldera. You would just think you're standing in low land. Underneath the Earth, we have a similar magmatic composition to Plinian eruptions. It's not by chance that we only very recently began to discover the gigantic calderas left over by past supervolcanic eruptions, that only 100 years ago were thought to be impossible to have occurred. The ability to view the land from above, from a helicopter or plane, and even more so via satellite imagery, led to the uncovering and identification of the scale of these types of volcanic eruptions, with more and more ultra-Plinian volcanoes being discovered every decade. These volcanoes form calderas due to the fact that during their enormous eruptions, instability that is generated causes the ground above it to collapse into the rapidly emptying magma chamber, which causes devastating pyroclastic flows. And if volcanoes of this scale are located in shallow water, mega tsunamis at a scale that is completely unimaginable can occur. These eruptions resemble a nuclear explosion with giant mushroom clouds that soar to heights that are at a minimum 80 kilometers or 49.7 miles when released. It is then carried by the trade winds, and it journeys forth to shroud a giant portion of the Earth, with the largest eruptions of this category being able to shroud the entirety of it. To give a quick example, because of atmospheric circulation patterns, eruptions can have an effect on the climate of both hemispheres of our planet, and the ash cloud is spread globally as it follows this circulation pattern and rides with planetary winds. This cloud can choke out vast areas of land and cause extinction level events at their most strongest. For a more accurate insight on the many ways it does this, check out my Campi Flegrei Part 4 video, where I cover what would happen if a supervolcano at the scale of some of the most largest in history erupted in modern day. You don't need to watch the other 3 videos to get into this, as the demonstration itself can be applied to any major supervolcanic eruption that is at a level akin to some of the most strongest that we know of in history. There is also a good example on how ash clouds are carried by planetary winds in this video. I'll pop a link to it in the description down below, just in case you want to check it out. Heads up, it is a long one, so in the description you'll find I've broken up the video into the various topics I cover, so you can skip ahead to what you want to see. So the sheer power involved is why these eruptions produce massive calderas instead of building stratovolcanoes. Fallout isn't able to accumulate to build up a mountain. It is instead either violently ejected tens to hundreds of kilometers away, or the eruption was so destructive that it spewed out extremely large amounts of magma, which destabilized the ground above these huge structures, and thus the surface collapsed within. So these eruptions are so immensely explosive that the depression formed from it made it impossible to follow the type of mountain building cycles we are so familiar with. Instead, eruptions like these very commonly form a lake, such as what is seen in present-day Lake Toba within northern Sumatra, or Lake Taupo in New Zealand's Northern Island. Another reason mountains aren't built from the largest kinds of these volcanic eruptions is because the eruptions themselves aren't common. They usually take tens of thousands to hundreds of thousands of years to build up the magma chamber, because of how vast and massive these magma chambers are. And they always culminate in gigantic eruptions. Even if the eruptions didn't have such a tremendous scale of explosivity, the viscosity of the magma itself renders it near static. It is so thick it has no ability to flow, and can't build the type of mountainous structure that other volcanic types are known to build. Supervolcanic eruptions cause immense changes to the weather, and the largest of them cause extreme volcanic winters, which can last for decades. This phenomenon is similar to what would occur following a nuclear war, and the ensuing nuclear winter that would follow, and it occurs because of the fallout that is released during the eruption, which shades and reflects incoming solar radiation whilst absorbing terrestrial radiation. I intend to make a video in the near future to explain this process in depth, but to be brief, sulfur dioxide is the main player in regards to the cooling of the climate. Following these types of events, as it moves into the stratosphere and combines with water, it creates sulfuric acid aerosols that go on to create a haze of tiny droplets in the stratosphere. These work to actively reflect incoming solar radiation, and they also absorb terrestrial radiation. There are other types of fallout released during these eruptions, which also contributes to this event, but sulfur is definitely the main player. So when this situation occurs, a rapid cooling of the Earth's surface soon follows. So, to summarize, there are 6 different magmatic eruption types, and the style of the eruption depends on a number of factors. The strongest factor is the silica level, which is based on the predominant rocks that inhabit a magma chamber. So, the magma chemistry, content, viscosity, and temperature forms the basis for how destructive or effusive a volcanic eruption will be. So, that wraps up the category of the differing magmatic volcanic eruptions. In the next video, we'll take a look at the 3 different types of phreatomagmatic eruptions, and we'll also discuss phreatic eruptions and what the difference is between the two. I hope you enjoyed this video. If you learned a few things, please like, subscribe, and share this video around. It really helps the channel out. I've just started using Instagram again, so consider following my account to get a hint at future videos and content. The link to this will be in the description down below. Thank you for watching. I'll see you all real soon.